So this lesson, it focuses on building reduction tables from data. When you get the data, you have to know what are your oxidizing agents and what are your reducing agents. And we're going to look to see if it reacts, the OA is above. If we don't have a reaction from the pairing, the OA is below. So, but what are the oxidizing agents? It really helps with speed, efficiency to know some patterns. So I'm going to color code these patterns. Red if they're always true, and red, you got to be a little more careful. These are mostly true, but there's a few exceptions. So I'm going to get started with looking at metal ions, metals that have a charge. And if we look for our metals with charges, we find a lot of them on the OA side. Almost all of our metal ions are oxidizing agents. Now, there are a few exceptions. You do see some metal ions on both sides. Like iron 2 is on both sides of your table. So looking at our table, I'm saying this side is where we find most of our metal ions, but I'm going to have to color code it in red because there are a few metal ions on this side. There's iron 2 as an RA, but there's iron 2 as an OA. So you see a metal ion, your first thought is it's probably an oxidizing agent. Now, when it comes to the elemental metals, you actually don't have any exceptions there. You never find elemental metals that are zero gaining electrons and becoming negative. All of our metal ions, we talked about gold, we've got silver, there's lead, and the bottom of the table has a whole bunch of group 1 and group 2 metals. So I've got my blue always pen. Now we want to keep looking for some more patterns. So I'm just going to pause and let you think. Do you notice any other trends in that table that we can summarize? So to highlight the last few trends, I'm going to flip back to my table. Now, if you scan the table for H plus or H plus with something else, so an acidic combination, you'll find you only see H plus. There's one on the acid side. There's H plus by itself. There's a bunch more, but you never find H plus on the RA side. And conversely, if you look for hydroxide, you only find hydroxide on the RA side. You only find it on the right. There it is by itself, but it also shows up in some pairings. So I'm going to highlight that. I'm blue. There's no exceptions to this. H plus or in a pairing. I'm not writing that. Okay. Hydroxide or hydroxide in a pairing is always an RA. Hopefully you can see where this is going to help you when you're scanning for things. You're focusing in on certain columns or certain parts of the table. If we focus in on the halogen sort of last, I'm going to clean this table up. You'll find there's diatomic chlorine, there's diatomic bromine, there's diatomic iodine. They're all on the OA side. All of their ide forms are all on the RA side, and there's no exception to that. So I've got to stick to my blue. There's no exceptions. You may want to expand on this, but all the INEs from group 7, chlorine, bromine, iodine are all oxidizing agents. All of those group 7s, when they end in "ide," they're all reducing agents. So I'll just stick in one example. Chlorine, 0 charge, OA, chloride, negative reducing agent. Probably the most useful, often used from this list is that when you see an elemental metal like lead, it is never an oxidizing agent. You don't even have to look it up. That's going to save you time, hopefully make you more successful, make less errors. And this is really going to help us with building a redox table. So let's sort of roll into our first redox table where we're going to see halogens, and then our next redox table we're going to have lots of metals. So we'll use the top trends to guide us a bit. So we've got 9 experiments here. I'm going to create a reduction table just like your Alberta 2030 data booklet. We've got bromine. When it was added to or mixed with bromide, there was no reaction. So you can maybe just put an X in your table to summarize that. When bromine and chloride were mixed, there was no reaction. But when bromine and iodide were mixed, we did have a reaction. This all tells us something about the OA-RA positioning. So the first thing I'm going to do is kind of lay out our answer. We're asked to build a reduction table. So I'm going to label it. Now we're going to have all our OAs on the left and our RAs on the right. So you don't have to write this, but it's a nice visual for our structure. Okay? Reduction table is GER, gaining electrons reduced. OA plus electrons makes RAs. Okay? And we need to get some ordering. Before we can start looking at that first red X and using that, we've got to figure out, is the top OAs or is the top RAs? There's no rule that says the columns or rows have to be certain species. So this is where our trends, our patterns can help us, or you could look at the charges, that being neutral, that being minus. When bromine turns into bromide, that would have to gain an electron to go 0 to -1. So 0, if you pick up an electron, if this gains an electron, or 2, I know it's a gaining, to become minus, so that means that this species was reduced, gaining electrons reduced. So what agent is bromine if it gets reduced? It gets reduced, it's the opposite agent, so that's an oxidizing agent. Which is the same trend if we realize that all our ion-y halogens were OAs, we maybe could have skipped that and saved some time. Okay. So you either have to figure out what's an OA or remember some patterns. Now the data, when it's given in columns, typically will have we'll have them grouped together. All of those that I circled are all neutral and are OAs, and these are all our minus species, and these are all our reducing agents. Okay, so we got to figure that out. Now I'm going to start going through some of the reactions, and I'm not going to need all 9. Okay. I'll use as many as I can until I can get an order. Our first, bromine, bromide, that would be like 2 that are in the same row. So that's not going to help us. I want to use some different species. Okay. I could use bromine and chloride, that data point. Okay. I've got the OA is bromine. It does not react with chloride. So you have to think of where would the chloride go? Is it going to go up or down when there's no reaction? That's our spontaneity rule. When the OA is above, there's a reaction. When the RA is above, there's no reaction. So we have no reaction, so I've got to go up to the other column to get to chloride. If I look at the bottom reaction, there was a color change. There was a reaction with bromine now. So that means bromine is going to go down to iodide. Well, I've already got a little bit of labeling of bromine. I'm going to rebuild on that, and I've got to go down to the other column to get to iodide. And just by looking at that first column, I've got an ordering already. I can build a redox table from the blue and then the blue-green combo that I analyzed. Okay. Things of chloride are on the top, bromine or bromide is in the middle, and iodine, iodide will be on the bottom. Then I can use some of these experiments to double check I've built the right table. Okay. So I'm going to start building that table. I've got 3 half reactions, one with chlorine, one with bromine, one with iodine. Let's see, I've got Cl minus on the top, that's an Ra. I've got bromine, that's an OA, that's next. The very bottom, I know that iodide is a reducing agent. Okay. And now I've got to complete all of these using my headings tell me the chemicals that are the OAs and the RAs. So I'm going to hide that a bit, but that's what I'm looking up to. Our chlorine-based OA must be diatomic chlorine. That's what's in one of our headings. For iodide, that must come from the OA iodine. Bromine becomes bromide in our RA column. Now I'm doing well so far, except for I didn't leave any room for electrons. So I'm just going to make myself some room. This might have been annoying for you. You can always write the electrons on the far right. Now I need to add, I'm going to balance these, and then I'm going to complete how many electrons I need. Okay? I'm building reduction tables. The electrons have to be at the beginning. Now I have 2 chlorine atoms, so they're going to have to make 2 chloride atoms. That's like Science 10 type of balancing rules. And then I got to think of how many electrons. Every chlorine is going 0 to -1. So that's a 1 electron difference, 0 to -1. But then there's 2 chlorine atoms. So the first chlorine transfers 1, the second chlorine atom transfers 1. So in total, there's 2 electrons. And all of these half reactions follow that same pattern in this particular example. 2 bromines, so we need 2 bromides. It's 0 to -1. So 1 electron for every bromine atom, there's 2 of them. So the 2 electrons covers the 2 gaining. Iodine, same thing. Okay. Let's do a little bit of checking. Let's look at chlorine and see if our table backs up. Chlorine is the best oxidizing agent in this table. Chlorine should react with bromide because it's below it, and chlorine should react with iodide because it's below it. Does our table say that? Chlorine does react with bromide, good. Chlorine does react with iodide, good. It just doesn't react with what's right across from it. It is not technically below. It's also not technically above. Something directly across will not react. The same way that if something is going to go downhill, it's going to be spontaneous. That's the OA above the RA. The RA being above is like something trying to go uphill, and that doesn't happen spontaneously. Something being right across from each other, a flat, is like something on a flat surface. That doesn't roll spontaneously. Okay, so even though it's even, it's not spontaneous. You have to give it a bump or a push. So things don't just move on flat surfaces. Or electrons don't move with OAs and RAs that are directly across from each other. Okay. So that's our first example. We're going to go right into a second one, and hopefully by the end of the second one, this makes a bit of sense. So when you're building reduction tables, you've got to label your chemicals, and then you're using the spontaneity rule. Reaction, OA above RA. So I'll summarize that. OA above the reducing agent is a reaction. When the OA is below and you have to go up and over, there is no reaction. That's the heart of what we're building on to answer these questions. Okay. So you can get a different set of information, same skill set, but instead of little boxes, we actually have 3 reactions, which would have been 3 boxes in the previous example. So we're going to build a reduction table, exactly the same heading as before. Cobalt ion reacted with indium. Copper 2 ions reacted with cobalt. But copper 2 ions do not react with palladium. Okay, there's no evidence of reaction. The bottom one is non-spontaneous. So we're going to go through these shortly. So the first thing I like to do is lay out the structure of our answer. We're asked to do a reduction table. I'm not going to write the OA and the RA headings in, but you may do that to cue your brain to keep yourself organized. Okay. Now, we could either spend about 2 minutes going through every reaction and figuring out what the OAs and RAs are, or if you remember the patterns, neutral metals, elemental metals are always, and what did I say? What was on that summary table, our first slide? Elemental metals are always, oh, and I wrote it wrong. Nobody corrected me. I wrote the lead right, but I wrote metal ion twice. Just our elemental metals are always reducing agents. So that's going to help us. The metal ions sometimes have exceptions, but we've got a elemental metal in every single one of these reactions, so there's no way they're anything but our reducing agents. I don't even really have to analyze them, which means the other ions have to be our OAs. That you can't have 2 reducing agents. You have to have an RA, you have to have an OA. Something's giving, something's taking. So we don't have columns, but we have some trends that help us. Okay. Going back to our spontaneity rule, the first one was spontaneous. So the OA is going to be above the RA. That's a reminder. Most of you won't write that out, but let's do it with our chemicals. Cobalt 2+. I don't care that there's 3 of them. I'm just taking the chemical. I'm going to have to go down into the right-hand RA column to get to indium solid. So that's going to order 2 of our half reactions. Our second reaction also is spontaneous, so the OA will be above the RA, and our OA is copper 2+. it's spontaneous reactions. We're going down and to the right, and that's when we're going to find elemental cobalt. Our last piece of information, copper 2 did not react with PD. So we've got the opposite OA-RA sequence, Cu2 plus, and I have to go up because of the no reaction. So we've got all the bits out, and now we've got to organize them all. What is on the top, what's in the middle, what's on the bottom. So that's what I'm going to that's what I'm going to do now. I'm not going to build the table yet. I'm going to do some planning. So let's see, I've got cobalt 2 plus. I know I have to have indium below it. And it can help to put in the pairings. Cobalt would make the elemental cobalt. Indium would have the indium 3 plus. This is my planning. I'm not going to bother worrying about the electrons yet. Okay, is there anything above cobalt? Well, there's our next. Cobalt has copper above it in the blue. So there's cobalt. There's cobalt. We have to have copper 2 plus above it. So, and that would make elemental copper. Then last, we can tie in our red colored reaction. There's copper 2, which I've just put in, and palladium must be above it. But we don't have any evidence of reaction to know what the OA to go with palladium would be. So you've got to use your periodic table and find what is the most common charge of PD. None of the ions would be spontaneous, but I'm going to put the most common, the 2 plus ion. So I looked at each reaction. I figured out what was above and below. I got my sequence, so now we can build our table. Put in our electrons. PD2 plus some electrons is going to make the elemental. Plus 2 down to 0. Well, that's 2 electrons would get it down to 0. Next is copper 2 plus to elemental copper. That would be 2 electrons again. Next, we're down to cobalt. Yet another 2 plus. Last, we have indium. Now, this is a 3 plus ion, so we're going to need 3 electrons. And that is our reduction table. It's all gaining electrons. Now, if you get this on a diploma, they'll ask you to probably do some ordering to do a numeric response or on a test. So you might have a question like this. List the RAs from the weakest reducing agent to the strongest reducing agent. So I'm trying to let you think, what column is that and where do I find the weakest? So what's our pattern? The strongest OA is top left. The weakest OA is bottom left. So those aren't our answers. Those are OAs. Reducing agents. The strongest is on the bottom. The weakest reducing agent is on the top. Now, what were we asked? List the reducing agents from weakest to strongest. That arrow would be our answer pathway. So that would be palladium. I'm going to leave the states out. Palladium solid, copper solid, cobalt solid, indium solid. And that's building reduction tables.